right, so we've talked about ionization and electronegativity today. So right now I want to talk to you about the different types of bonds, okay? Now, in chemistry, in high school chemistry, we're going to deal with these three different types of bonds, okay? We're going to deal with bonds that are called ionic bonds, okay? And then we're going to deal with bonds called metallic bonds. And then we're going to deal with bonds called covalent bonds, all right? Now, you don't have to write this down yet. I'm just kind of getting... Ionic bonds occur between a metal and a nonmetal. Metallic bonds are weird. We won't even write formulas for them. They occur amongst metals themselves, okay? And then covalent bonds are when atoms, nonmetals, share electrons with each other, okay? And you can see sharing written in here, share. And which electrons do you think are shared? Yeah, the valence electrons. So this means share valence electrons. So first we're going to talk about ionic bonds, okay? And it's pretty simple stuff. All right, we're looking right here at ionic bonds. Ionic bonds occur between a metal and a nonmetal. One atom gains an electron, and one atom loses an electron, okay? So they occur between a metal and a nonmetal. And one atom gains an electron, and one atom loses an electron. Earlier in class, in the last video, I showed you lithium and fluorine, and I'll show you lithium and fluorine again, okay? I think those are the two I showed you. Ionic bonds, okay? So first, if we're talking about ionic bonds, the little saying I like to say is, if you look up here, here are metals, right? Here are the stairs. Everything on this side of the stairs is a metal. All right? Okay. All right, everything on this side of the stairs is a metal. And then everything on this side of the stairs is a nonmetal. So if an ionic bond occurs between a metal and a nonmetal, here's the thing. Ionic bonds cross the stairs. And look on my green chart, there's even an arrow that goes across the stairs and it says ionic, crosses the stairs. So anytime you cross the stairs and you look into a formula, that's an ionic compound. Now, H doesn't always count. H can sit right here on the periodic table because it only needs one more valence electron, right? Just like fluorine, you know these guys have 7 valence electrons and they'd like to have 8. Hydrogen has 1 and it would like to have 2. So sometimes it sits right here. And you've also noticed early in class, sometimes helium can sit right here. Does that make sense? So anytime you cross the stairs, except with some examples with H, anytime you cross the stairs, that's an ionic bond. So let me show you an ionic bond happening. All right? Here is lithium. It's chilling out, doing nothing on a Saturday. It's neutral. And here is fluorine. 1, 2, 3, 4, 5, 6, 7. Here's fluorine. Fluorine is very electronegative. Lithium has a low ionization energy. That's a combination for an ionic bond. Fluorine will take this electron from lithium. Lithium has now lost its electron. Now lithium is much smaller, and it's a +1 cation. And now fluorine, oh my Lord, I did that whole thing and they couldn't see it. Oh, I'm sorry everybody, I'm going to start over. People at home, I'm going to start over. Ready? Here's lithium hanging out. Here's fluorine. Fluorine is very electronegative. Lithium has a low ionization energy. Fluorine will take that electron from lithium And now fluorine will be -1. Lithium has been ionized. They've both been ionized. Lithium has been ionized. It has shrunk greatly. Now it's lithium +1 and fluorine -1. This is a cation. This is an anion. And we have an ionic bond between these two. That's what an ionic bond is when the atoms are ionized. Does that make sense? This happens anytime atoms that cross the stairs bond with each other. And if you notice, I used fluorine and lithium. And they cross the stairs. Does that make sense? All right. Really quickly, let's talk about things that are bonded ionically. Okay? If we look at this, the question sometimes can be this simple. Which combinations of elements would most likely form an ionic compound? That's right. And I watched Lily, I watched you like, that's what I want to see. When I ask you people at home a question like this, you need to look at your periodic table and see which ones are crossing the stairs. The one that are obviously crossing the stairs, sodium and fluorine. There's your ionic compound. Remember I told you hydrogen doesn't always count, right? Okay. So ionic bonds are very strong. And this is a word you want to write down, a crystal lattice. Ionic compounds form a crystal lattice of ions. And that is a very strong structure. And the structure has some very predictable behaviors, physical behaviors. Okay? So ionic compounds form what we call a crystal lattice. And here's how I can best describe a crystal lattice to you. If you've ever seen a fence like this is called a lattice fence, okay? And lattice fence are made of very thin pieces of wood that aren't that big a deal. And they're only stapled together with little staples. But they're very, very strong because this pattern repeats over and over and over and over and over. So the strength of this lattice is the bond angles and the multiple consistent bonds occurring, right? So if we stacked a bunch of sodium and fluorine atoms perfectly like this, then the bonds they form between each other form a very strong solid. And when I'm saying they form a very strong solid, when I say they form a very strong solid, I mean it's a solid that has these properties. Ready? Here are the properties that you want to know for ionic bonds. They have high melting points. They are soluble in water. Now that doesn't mean all liquids. They're soluble in water. They're usually a solid at room temperature, and they're good at conducting electricity. They're good at conducting electricity when in water, when dissolved in water. All right. So these are the properties of ionic bonds. So here's what I've said to you about ionic bonds. They form between atoms that cross the stairs. Okay, just put these things together because I'm about to make a big statement. Ready? Ionic bonds, here's what I've said about them. They form between atoms that cross the stairs, and they involve an electron being taken from one atom and given to another. Okay? And they form a crystal lattice. Now, the exact opposite of this is a covalent bond. Okay? So all the traits of these ionic bonds and the way that it's done is the opposite for covalent. So if you can remember one, you'll know the other, because the other is the opposite. Let's go here and let's talk about a covalent bond. Covalent bonds occur between two or more nonmetals, okay? So if we're looking up here on the periodic table, covalent bonds occur between these guys. If you're sticking nitrogen and oxygen and carbon together and you're making a molecule, these things form what we call molecules. If you're making a molecule out of these atoms, then that's covalently bonded. Okay? And you remember I said it was the opposite of an ionic bond. Well, ionic bonds cross the stairs. Covalent bonds do not cross the stairs. It's the opposite, right? Covalent bonds do not cross the stairs. Remember I said that ionic bonds occur when one atom steals an electron from another. A covalent bond is formed by sharing electrons. Okay? And they're very strong. They're even stronger than ionic bonds. Boy, that's some terrible English, even more than ionic bonds. Well, I don't know, it's not too bad. Ionic bonds form very strong solids. And by this I mean they have high melting points and they conduct electricity and dissolve in water. But covalent bonds themselves between atoms are much stronger than ionic bonds. And we'll talk about that a little bit later. So when we talk about covalent bonds being the opposite of ionic bonds, right? Ionic bonds involve taking electrons from each other. Covalent bonds involve sharing. Ionic bonds involve crossing the stairs. Covalent bonds occur between two nonmetals, so you don't cross the stairs, right? Well, let's talk about their traits, all right? When things are covalently bonded, we call them molecules, right? That's what a molecule is. NaCl, that crosses the stairs. That's not a molecule. There's no such thing as a molecule of salt. But there is a molecule of carbon dioxide. Let's take a look up here. See how salt is sodium and chlorine? It crosses the stairs. That's ionic. It's not a molecule. But if you made some carbon dioxide, that doesn't cross the stairs. These are molecules, okay? The salt that crosses the stairs will be a solid at room temperature with a high melting point. Carbon dioxide is obviously a gas at room temperature with a low melting point. Everything is the opposite, okay? And when we go down here and we look at the traits, okay? Look at this is your last note real quick. Covalent bonds are weaker, and that's really worded wrong. Well, and I'll tell you why it said this. Covalent bonds are stronger, but it's in a different way. Stronger, but, and you'll understand why this used to say that in just a second. Covalent bonds are stronger, but molecules have lower melting points. They're usually a gas or liquid. They're often insoluble in water, and they don't conduct electricity. So if you look, these things are total opposites, all right? These two are total opposites. Ionic bonds, solid, high melting point, good conductor. Covalent bonds, gases or liquids, low melting point, poor conductor. And we can do a really cool example right here for the people at home. All right. People at home and people here. Just for fun. I have some distilled water. Okay? Now, water is a molecule. Water is covalently bonded because the H, remember the H does not count as crossing the stairs, correct? So water is a liquid at room temperature, and water does not conduct electricity. You're like, what? Mr. Perkins, water conducts electricity? It doesn't. Watch. I'm going to touch. This is a raw wire that goes to the radio. When I touch it together, you can hear the radio. But when I put it in water, the radio's not on. I can even put my finger down in here, and I'm not getting shocked. Okay? So why is that, Mr. Perkins? Well, because water itself doesn't conduct electricity. It's the thing we put in the water. Now, if I put something in the water that's covalent, and covalent things do not conduct electricity or even usually dissolve. Look, I'm going to put a little sulfur down in here. Sulfur is covalent. The formula for sulfur is basically S8. It does not cross the stairs. The sulfur doesn't even dissolve in the water, much less conduct electricity, right? But when I put some, this is probably baking soda, yeah, when I put some baking soda, this is made of sodium and carbon and hydrogen and oxygen, and this crosses the stairs, okay? I'll put some of this in there, it's totally different. This stuff conducts electricity in water. Does that make sense? Now, the last thing I'll tell you is, there is a word for a compound that dissolves in water and conducts electricity. You know this from drinking sports drinks. Davis, what is the word for a compound like salts that dissolve in water and conduct electricity? Therefore, you would want to drink them and keep from getting cramps. Anybody know? Electrolytes. Have y'all heard that term? Right? That's what's in Gatorade, right? And that's why Gatorade has that salty taste. Gatorade doesn't taste like soda, right? So electrolytes. So there you go. Compounds that cross the stairs, ionic compounds, are electrolytes. You don't want to drink them all, but, you know, it's good if you drink the right ones. Does that help? Okay. Now we're going to do a cool lab. And hopefully this thing's still recording. All right.